So imagine you could somehow step completely outside the universe right now.
Right, like taking a true God's eye view of everything.
Exactly. You just pull yourself out of the fabric of reality, turn around and look back at the whole thing.
You'd probably expect to see this massive, swirling cosmic dance, right?
Yeah, exactly. You'd expect stars exploding, planets spinning, galaxies colliding. But according to the most fundamental equations in modern physics, you wouldn't see any of that.
No, you really wouldn't.
You would see a perfectly frozen block of ice. I mean, nothing moves, nothing evolves, nothing changes.
Which is completely, entirely counterintuitive to everything we experience.
Right, because here you are, listening to this deep dive, actively feeling the seconds tick by on your watch, anticipating the next word I'm going to say.
You are viscerally experiencing time.
Yes. So today, we are going to figure out how your brain is actively hallucinating the concept of time.
It really forces a complete rewiring of how we perceive our own existence, honestly.
It really does. Because we are unpacking a massive stack of theoretical frameworks today.
Yeah, we're tracing a path straight from the historical breakdown of classical physics right into the radical frontiers of quantum information.
We're looking at quantum temporal flux. And the core mission here is to figure out if time is actually a fundamental feature of the cosmos, or if it's just, an elaborate mirage.
A mirage generated by quantum states and thermodynamic blurring, yeah.
Okay, let's unpack this. Because to understand why time might be an illusion, we first have to look at the catastrophic scheduling conflict at the heart of physics.
Oh, it is a massive conflict.
Right. I was looking through the background material on the problem of time, and it seems like the crisis really started when physicists tried to force general relativity and quantum mechanics to, talk to each other.
They essentially have mathematically incompatible views on what a clock even is.
Which is wild.
It is. Think about how the giants of physics treated the concept. You have Isaac Newton, right?
The Apple guy.
Exactly. He built classical mechanics on the idea that time is absolute, like an invisible river.
Just flowing uniformly forward, completely ignoring whatever's happening inside it.
Right. It's a rigid external parameter. But then Einstein completely obliterated that notion.
Because general relativity made it malleable.
Exactly. Einstein demonstrated that time is woven together with three-dimensional space.
Into space-time.
Yes, the four-dimensional manifold. Gravity isn't just a pull, it's the curvature of that manifold.
So mass and energy dictate how space-time curves.
Right. And that curvature dictates how mass and energy move, which means the rate at which time passes is entirely dependent on your local gravitational field and your velocity.
Right. Time became this dynamic, active player in the game.
Which works beautifully for the cosmos. Black holes, galaxies, the Big Bang.
But then, and this is where I got stuck, the moment you zoom down to the subatomic level, time just reverts back to Newton's river.
It does. In quantum mechanics, time suddenly reverts back to behaving like a rigid parameter.
Like it's just a dial sitting on the outside of the experiment.
Precisely. In the Schrödinger equation, the wave function of an electron evolves through time, but the electron doesn't warp or interact with time itself.
So you have this bendy, dynamic time at the macro scale and a stiff external time at the micro scale.
Which creates an immediate paradox when you try to unify them.
Because you need them to unify to understand, like, the center of a black hole, right?
Yes, or the exact moment of the Big Bang. You need a mathematical framework that applies quantum mechanics to the gravitational field itself.
And physicists try to do this, right? Canonical quantization.
Yeah, in the mid-20th century, they essentially tried to take the geometry of space-time and treat it as a quantum state.
Okay.
And this led John Wheeler and Bryce DeWitt to derive an equation that governs the wave function of the entire universe.
The Wheeler-DeWitt equation.
That's the one.
In the texts, it is written pretty simply. It's the Hamiltonian operator h hat acting on the wave function of the universe, psi, and the whole thing equals 0.
Which sounds simple, but the implications are terrifying.
Well, let me make sure I'm translating the math correctly here. In quantum mechanics, the Hamiltonian operator is the thing that dictates the total energy of a system, right?
Yes, it's the energy operator.
And because energy and time are conjugate variables, the Hamiltonian is basically the mathematical engine of change. It tells you how the quantum state will evolve from one moment to the next.
That is the standard interpretation, yeah. Applying the Hamiltonian to a wave function gives you its time derivative.
But in this equation, it equals 0.
Exactly. Applying the total Hamiltonian to the universal wave function yields absolute 0.
Meaning the time derivative vanishes.
Yes. Mathematically, this implies that the wave function of the universe does not evolve. It does not change.
At all.
Not at all. There's literally no parameter t for time in the fundamental equation of quantum gravity.
So this is the frozen formalism I kept reading
I think
about.
that's the term for it, yeah.
So if you take that ultimate, objective, God's eye view of reality, it is just a single, unchanging quantum state.
Just a frozen block.
Okay, I have to push back on this frozen universe concept, though.
I figured you might.
Because if the underlying math of the cosmos has a time derivative of 0, why did I have to wait in line for 10 minutes to get my coffee this morning?
A very practical question.
I mean, I physically felt the time passing. My coffee lost heat. Things clearly happen in my reality.
They absolutely seem to, yes.
I read this analogy in our sources, comparing it to a computer system. It's like the reality we inhabit is running on a base operating system where scheduling.x was just never installed.
That's a great way to put it.
But the software on top, like our daily experience, is constantly generating deadlines and progress bars anyway. How do we square a mathematically static universe with cold coffee?
Well, that tension is basically the defining philosophical crisis of modern physics.
It's not just a math error.
No, it's not a rounding error. If the Wheeler-DeWitt equation is accurate, then our daily visceral experience of time passing must be an emergent phenomenon.
Emergent, like it's not in the base recipe.
Exactly. It's not an ingredient in the base recipe of reality. It's a flavor that only arises when you mix the ingredients and taste them from a very specific, limited vantage point.
Okay, which brings us to the theoretical physicist Carlo Rovelli.
Yes, Rovelli has a brilliant take on this.
He essentially argues that the flavor of time only exists because we have a terrible sense of taste.
Huh. That's one way to frame it.
Like, we are physically incapable of perceiving the universe as it actually is.
Right. Rovelli's thermal time hypothesis shifts the burden of time completely away from the universe itself and puts it onto you, the observer.
So it's my fault I was late for work.
Basically. He argues the distinction we make between the past and the future, the arrow of time, is deeply tied to thermodynamics.
Specifically entropy, right?
Yes. Entropy is, broadly speaking, a measure of disorder. And the second law of thermodynamics dictates that in an isolated system, entropy always increases.
Things get messier.
Exactly. And that gives time a direction. But Rovelli points out a crucial fact. Entropy is a purely macroscopic concept.
Oh, right. Because if you look at, say, a single molecule of water, it doesn't have a temperature.
Exactly. It just has kinetic energy, a specific velocity and trajectory.
So temperature and heat and entropy, they only emerge when you zoom out and average the behavior of trillions of water molecules bumping into each other.
Precisely. And Rovelli is applying this exact concept of statistical blurring to time itself.
Oh, okay.
Think about it. The universe is this staggeringly complex web of quantum microstates, countless particles fluctuating, superposing, entangling all at once.
And I definitely can't see all of that.
No. You and I, as macroscopic biological organisms, do not possess the sensory or computational capacity to register the exact position and momentum of every single quantum particle around us.
We only interact with the macroscopic averages.
Right. We interact with a coarse-grained reality.
It makes me think of a hyper-realistic, microscopic, pointillist painting. Like
Yep.
we're standing 50 feet away from it.
Yes, a perfect analogy.
We just see these broad strokes of color. We see a chair, a cup of coffee, a moving car. But we are totally blind to the billions of discrete, static dots of paint that actually make up the canvas.
And because of that blindness, because of our coarse graining, we are fundamentally ignorant of the true microstate of the universe.
Ignorant.
Yes. And in quantum statistical mechanics, this lack of information is mathematically represented by a density matrix, which describes a mixed thermal state.
Okay, I'm tracking.
Rovelli utilizes something called the Tomita-Taksaki theorem, which is this incredibly complex piece of mathematics from algebraic quantum field theory.
Let's try to keep the math approachable, though.
Fair enough. Essentially, that theorem demonstrates that any thermal state, any state of statistical ignorance inherently defines a one-parameter group of automorphisms.
Okay, you lost me a little with automorphisms.
Simply put, the math of our own ignorance naturally generates a mathematical parameter that behaves exactly like flowing time.
Wait, so the math of us not knowing the exact details creates a variable that looks like time.
Exactly. What's fascinating here is that time is revealed to be an expression of our incomplete knowledge.
That is wild.
The flow of time is not a physical river carrying you forward. It's the statistical boundary created by the limits of your own perception.
But if I had, like, a super brain, sensory apparatus capable of perceiving the exact quantum microstate of the entire universe simultaneously.
If you could see every single dot in that pointillist painting at once,
The blur of entropy would vanish.
and the mathematical parameter for time would disappear entirely.
Yeah, I'd just be staring at that static, timeless reality from the Wheeler-DeWitt equation.
You'd be staring at the frozen block of ice.
Okay, I understand how our macroscopic blurring generates the feeling of a thermodynamic arrow of time.
Yeah.
But I have a problem with this.
Go for it.
Ravelli's theory relies so heavily on the existence of an observer. It requires someone to have that coarse-graining perspective to generate the temporal flow.
It does.
So what about the universe before biological observers existed? What about the Big Bang? If time is just statistical ignorance, it feels like we are sidestepping the actual objective geometry of the universe.
That is a very valid critique.
Because I want a structural answer. And it seems like to find a purely mathematical, structural answer to the problem of time, we have to turn to Julian Barber.
Yes, Julian Barber, he completely discards the thermodynamic approach.
He doesn't care about the observer's ignorance.
Not at all. He reconstructs the universe from a purely relational geometry using a concept known as shape dynamics.
Keep dynamics.
He asks this terrifyingly simple question. If you strip away all invisible background frameworks like absolute space or absolute time, what is the absolute minimum amount of mathematical information required to describe physical reality?
And his answer is this thing called Platonia.
Platonia.
It sounds like some esoteric realm from a fantasy novel. But the sources define it as the ultimate universal configuration space.
To really wrap your head around Platonia, you have to imagine freezing the universe in an infinitely thin slice of a moment.
Okay, paused.
Right. Now, record the exact relative distances and angles between every single particle, every photon, every quark in existence.
But I'm not mapping them onto an XYZ grid, right?
No, absolutely not. You do not map them onto an invisible coordinate grid of space. You just map their geometric relationships to one another.
Like a massive web of connections.
Exactly. That singular, infinitely complex geometric shape is one configuration. And Barber calls this a now.
The capital N now.
Yes. Platonia is the massive mathematical landscape that contains every physically possible configuration. Every possible now.
So there is a point in Platonia representing the universe exactly as it is this exact second as you were listening to this.
Yes. And there is another point in Platonia representing the universe with just one single electron shifted a millimeter to the left.
And there's a point representing the Earth totally covered in magma.
And a point representing a cold, dead cosmos filled only with black holes.
And critically, this is the part that melted my brain. None of these nows are connected by time.
No. There is no evolution between them.
The universe covered in magma doesn't, become the universe we live in today. All of these configurations just exist. Permanently and simultaneously.
As static geometric points within this massive mathematical landscape.
I kept thinking about the bookshelf analogy from the readings. Platonia is an infinitely massive library.
Yes, the library of all possible universes.
And the shelves are stocked with books containing every possible narrative, every possible history. When you pull a book off the shelf and read it, you perceive a flowing narrative, right?
Right. Character A makes a decision on page 10, which causes a reaction on page 20.
You experience sequential time. But the physical book itself is utterly static. All the pages exist at once. The flow of the story is generated entirely by the sequential way you process the information.
It is a profound conceptual leap. It replaces the dynamic evolution of physics with the static exploration of a mathematical phase space.
But it demands that we answer the most obvious human objection.
Oh, absolutely. The memory problem.
Yes. If the past does not physically exist, if there is no flowing river of time connecting yesterday's configuration to today's configuration, how do you remember eating breakfast?
Or how does the Earth hold the fossil record of dinosaurs?
Right. If my current now is totally disconnected from yesterday's now, memory shouldn't be possible.
Barber answers this with the concept of time capsules.
Time capsules.
A time capsule is any highly structured static arrangement of matter within a single. Now that encodes a pattern we interpret as a history.
Okay, let's use the dinosaur fossil example.
Perfect.
We look at a Tyrannosaurus femur embedded in a cliff face, and our brains instantly generate this sprawling dynamic history.
We imagine the creature running through a Cretaceous jungle, dying, being covered in mud.
The mud compressing over millions of years into rock, tectonic plates pushing that rock up to the surface, we infer massive amounts of time.
But physically, objectively, what actually exists right now?
Just the rock.
Yes. What exists is a highly specific static arrangement of calcium, carbon, and silicate minerals existing in the exact configuration of your current now.
So the history is just a cognitive deduction. It's derived entirely from the structure of the present.
Exactly. And Barber argues that human memory works the exact same way.
So my memory of eating breakfast isn't me, like, accessing the past.
No, the past is gone.
Yeah.
Or rather, it's just a different inaccessible coordinate in Platonia.
So my memory is simply a specific static pattern of synaptic connections and chemical gradients existing in my brain right this very second.
Your brain is a time capsule.
The feeling of the past is literally coded into the geometry of the present.
The sources offer a beautiful metaphor regarding a bell, actually.
Oh, right, the bronze bell.
In Barber's view, the physical shape of a bronze bell is completely static. It is fixed, timeless geometry.
But when you strike it,
When struck, that static shape governs how it vibrates, and what we perceive is a rich, dynamic, evolving sound.
so the sound, the perception of change in time, is not a separate external ingredient added to the bell.
No, it is the subjective experience of the bell's underlying timeless geometry.
Platonia is the bell. We are just experiencing the ringing.
Wonderfully put.
But, okay, this raises a massive statistical problem for me.
Let's hear it.
Platonia contains every possible configuration, right?
Every single one.
So it contains nows that are completely chaotic, where my brain is just a cloud of disorganized plasma.
Lots of them, yes.
So why do we consistently find ourselves inhabiting these incredibly highly structured, logical time capsule nows? If it's just a landscape of disconnected moments, shouldn't my next now be just a random jumble of static?
This is where Barber introduces the concept of the lopsided geometry of Platonia.
Lopsided geometry.
He theorizes that the phase space itself is not uniform. It is highly asymmetrical. It funnels down to a point of ultimate geometric simplicity.
Like the Big Bang.
Analogous to the Big Bang, yes, he calls it the alpha point. Because of this non-uniform structure, the mathematical probability distribution within Platonia is heavily skewed.
Okay, meaning some nows are more likely than others.
Exactly. The quantum mechanical rules governing this landscape naturally concentrate probability amplitude around highly structured, internally consistent configurations.
So the laws of physics aren't telling things how to evolve over time.
No.
The laws of physics are just the rules of probability dictating which static shapes in Platonia are allowed to be brightly illuminated and which ones remain in the dark.
Exactly. Time capsules are simply the most mathematically probable configurations within the asymmetrical geometry of Platonia.
Okay, that handles the geometry. But it leaves us hanging on the physical mechanism.
How so?
Well, if reality is a collection of frozen static moments, how do the laws of quantum mechanics actually glue them together to simulate a continuous flow for the observer?
Yeah.
Even if motion is an illusion, there must be a mechanism driving the simulation. And here's where it gets really interesting, because we have to dive into the Page-Wooders mechanism.
Formulated in 1983 by Don Page and William Wooders. This framework provides the exact mathematical mechanism for deriving dynamic evolution from a static universe.
And it relies on, like, the weirdest phenomenon in physics.
Entanglement.
Yes. Einstein called it spooky action at a distance.
Two quantum systems interact and become linked in such a way that the quantum state of one cannot be described independently of the state of the other.
Even if they are separated by light years.
Right. Measuring the spin of particle A instantly tells you the spin of particle B.
So how did Page and Wooders use this to invent time?
Well, they realized that entanglement could solve the Wheeler-DeWitt paradox. They accepted the premise that the universe as a whole is a static, timeless quantum state.
Resting in that zero-energy Hamiltonian.
Yes. But they noted a crucial operational fact. Observers do not exist outside the universe.
Right. There is no external vantage point. We are embedded inside the wave function.
So mathematically, they took the total Hilbert space of the universe, which is the mathematical space containing all possible quantum states.
Okay.
And they divided it into two subsystems using a tensor product structure. They designated one subsystem as the clock and the rest of the universe as the system.
Wait, they just arbitrarily cleaved the frozen universe in two.
Operationally, yes. And crucially, they assumed that the clock and the system do not interact directly. They don't exchange energy.
But they are entangled.
Because they are both parts of the same overarching universal wave function, they are deeply quantum mechanically entangled.
Meaning the state of the clock is inextricably linked to the state of the system, even in a totally frozen universe.
Now imagine you are an internal observer, you are part of the system, and you are entangled with the clock. Page and Wooders prove that if you condition the state of the system on the measurement of the clock, the system mathematically appears to evolve.
Okay, I want to break down conditioning the state for a second.
It means you ask the mathematical question, what is the state of the system given that the clock reads time t1?
Right.
And then you ask, what is the state of the system given that the clock reads time t2?
And what did they find?
Page and Wooders demonstrated that the sequence of these conditional states perfectly obeys the Schrödinger equation.
Unbelievable.
The internal observer perceives unitary dynamic evolution. The system appears to change over time.
But if someone could step outside the universe and measure the combined global state of the clock and the system together,
They would see absolutely no change. The total energy remains zero. The global state is static.
so time emerges entirely as a relational property between entangled subsystems.
It is literally evolution without evolution.
Time is just a matter of perspective driven by quantum correlation. I was trying to map this onto a real-world concept, and I thought about a massive corporate group project.
I love this analogy.
Imagine this massive, multi-departmental undertaking. From the outside, the CEO just pulls up the final project folder on the server. To the CEO, the project is just a static, completed deliverable. It has no time component. It just exists as a whole.
The CEO is viewing the global Wheeler-DeWitt state.
Right. But for the people inside the team, the internal observers, that project was a dynamic, agonizing evolution. There were drafts, missed deadlines, late-night revisions.
The struggle?
Exactly. The time of the project only existed because you were constantly exchanging emails and draft with your team members. You measured your progress relative to their progress.
You were entangled in the collaboration.
Yes. If you cut the Wi-Fi, if you break the entanglement, the flow of time for that project completely stops for you.
That maps beautifully onto the physics. And what makes the Page-Wooders mechanism so extraordinary is that it is no longer just a mathematical parlor trick.
It's real physics.
It has been physically verified in a laboratory.
Yes. The Turin experiment. This blew my mind. Conducted between 2013 and 2015 by Ekaterina Moreva and her team in Italy.
The sources detail how they literally built a microscopic static universe on an optical bench.
How do you build a universe on a bench?
They utilized a process called spontaneous parametric down conversion.
Which does what?
It generates a pair of perfectly entangled photons. They designated one photon as the clock and the other as the system.
But how does a single photon act as a clock? You can't exactly stick hands on it.
You use its polarization. They pass the clock photon through a birefringent plate.
The crystal.
Yes, a crystal that rotates the photon's polarization as it travels. The angle of polarization acts as the ticking hand of the clock.
Clever.
They then designed an experiment to measure the system photon.
And here is where they proved the dual nature of reality.
Exactly. When they set up detectors to measure the system photon conditional upon the polarization state of the clock photon simulating the internal observer.
The team member inside the project.
Yes. They recorded the system photon evolving. They watched it undergo a measurable change, perfectly mirroring the Schrödinger equation.
They literally witnessed time flowing.
But then they brought in the CEO.
The outside observer.
They set up a different measurement, an interference measurement, that observed the global state of the two entangled photons simultaneously without referencing one against the other.
And what happened?
From that global super-observer perspective, the interference pattern demonstrated that the combined system was entirely static.
The polarization didn't evolve.
Time completely vanished. They experimentally confirmed that time is an emergent illusion generated by quantum entanglement.
It is arguably one of the most profound experiments of the 21st century.
Without a doubt.
But reading further into the sources, I noticed the physics community didn't just accept this and go home. They immediately started poking holes in the concept of the clock.
Physicists love poking holes.
Because in the Turin experiment, they used pristine, perfectly calibrated photons. But in reality, physical clocks are messy.
Very messy.
They require energy, they degrade, they have limits. What happens to the Page-Wooders mechanism when our quantum clocks aren't infinitely precise?
This is where the theoretical debate gets incredibly dense. Physicist Carol Kachar leveled three major criticisms against the original Page-Wooders paper.
What was his main issue?
He argued that if you try to take multiple sequential measurements using a physical clock, the math breaks down.
Well, why? Why can't I check my watch twice?
In quantum mechanics, observing a system alters its state. This is wave function collapse. Kucha pointed out that if you measure the clock, the resulting collapse might push the overall state out of the zero-energy Hamiltonian constraint.
So by measuring the clock, you accidentally inject energy into the system.
Exactly, breaking the rule that the universe must remain globally static. Furthermore, he argued the mechanism yields the wrong quantum propagators.
Meaning?
The probabilities for how the system should evolve between measurements get completely scrambled.
So the beautiful entanglement theory falls apart the moment you actually try to use it in the real world.
To salvage the theory, physicists developed two competing mathematical frameworks: the twirled observable approach, or TO, and the purified measurement approach, or PM.
Okay, let's break down how these fix the measurement problem, starting with TO.
The twirled observable approach is highly abstract. Instead of treating a measurement as a disruptive physical event, it constructs special mathematical operators that are time translation invariant.
Time translation invariant. Okay, what does that actually do?
It essentially integrates the measurement over all possible clock readings simultaneously, ensuring that the act of observing never kicks the system out of the static Wheeler-DeWitt state.
It mathematically guarantees the universe stays frozen, regardless of what the internal observer does.
Yes.
But the sources noted a major operational flaw with this approach.
The flaw is that to perfectly implement a twirled observable, your clock must be ideal.
Meaning perfect.
It must have an infinite spectrum of energy states to perfectly distinguish between infinitesimally close moments in time.
Which is physically impossible. You can't have a clock with infinite energy.
Exactly. Therefore, many theorists prefer the purified measurement approach.
The PM approach.
The PM approach doesn't abstract the measurement away. It physically models it. It introduces a third quantum subsystem into the math called an ancilla.
An ancilla, like an auxiliary memory drive.
Precisely like a memory register.
Right.
When the clock is measured, the ancilla physically interacts with the system and records the outcome. The state of the system becomes entangled with the memory register. By including the physical memory of the observer in the global quantum state, the PM approach successfully models sequential measurements without violating the static Hamiltonian constraint.
Okay, so we add a hard drive to the observer and the math works. But the sources highlight a massive consequence when you combine the PM approach with a non-ideal clock.
Ah, yes.
If your clock has finite energy and bounded resolution, the evolution of the system goes haywire.
The math gets very dark here. If the clock cannot perfectly resolve the distance between two moments, the system's evolution becomes time non-local.
Time non-local, meaning the state of the system right now depends on interactions that happened in the past or will happen in the future.
Essentially. The evolution equations become non-unitary, meaning they lose predictability and become probabilistically messy. Information seems to leak out of the predictable timeline.
That sounds bad.
Even worse, finite clock resolution leads to an indefinite temporal order.
Meaning you can't tell which event happened first.
Imagine two quantum events, A and B, occurring very close together in time. If your clock's fundamental tick rate is slower than the gap between A and B, the clock cannot distinguish their sequence.
Wow.
The universe itself cannot definitively say whether A caused B or B caused A. The strict chain of causality smears into a quantum superposition.
If the timeline smears, the whole structure of reality breaks down. How do theorists resolve this? How do we save causality if our internal clocks are imperfect?
The proposed resolution is a fundamental rewriting of the fabric of spacetime. To restore unitary evolution and a definite causal order when dealing with non-ideal clocks, the mathematics demands that time cannot be a continuous, infinitely divisible parameter.
It can't be a smooth river.
No, time must be discrete.
Time must be pixelated.
It implies the existence of a fundamental temporal graininess, likely at the Planck scale.
Which is tiny.
Roughly 10 to the minus 43 seconds.
I kept thinking about the refresh rate on a computer monitor.
Oh, that's a good comparison.
When you play a high-end video game, the character's movement looks perfectly smooth and continuous. But you know the GPU is actually rendering like 120 discrete, static frames every single second.
And your brain smooths it out.
The continuity is an optical illusion created by the high frequency of the discrete updates. Are we saying the universe itself runs on a cosmic frame rate?
That is the exact implication. The universe ticks forward in indivisible quantum jumps. The continuous flow we perceive is just the macroscopic blurring of trillions of discrete Planck-scale updates happening every microsecond.
That resolves the clock resolution problem. But it brings up an immediate conflict with Einstein.
Special relativity.
Right. We know from general and special relativity that time is relative. If I take my pixelated quantum clock, put it on a rocket, and accelerate to near the speed of light, time should dilate.
It should slow down relative to an observer on Earth.
Does this discrete, entangled Page-Wooder's mechanism survive the extreme relativistic physics of a near-light speed rocket?
It is a critical stress test for the theory. Recent research analyzed the Page-Wooder's mechanism under Lorentz transformations, which are the mathematical rules of special relativity.
Yeah.
They found that the mechanism holds up perfectly.
How? How does the entanglement survive the time dilation?
When you accelerate a quantum system to relativistic speeds, the system undergoes a mathematical transformation known as a Wigner rotation.
A Wigner rotation.
The boost in velocity fundamentally alters the internal quantum state of the particles.
So the acceleration physically twists the quantum state.
It rotates the degrees of freedom, like the spin of an electron. What the physics shows is that this Wigner rotation precisely recalibrates the entanglement between the clock and the system.
It recalibrates the entanglement.
Yes. The internal correlation shifts in such a way that the perceived ticks of the clock slow down for the accelerated observer, exactly matching the time dilation predicted by Einstein.
That is incredibly elegant.
The discrete relational time of Page-Wooder's successfully reproduces the macroscopic physics of special relativity.
Okay, let's take a breath and synthesize this journey so far, because this is a lot.
It is a dense conceptual stack.
We started by freezing the universe entirely with a Wheeler-DeWitt equation. We learned from Rovelli that our thermodynamic ignorance creates the illusion of flow.
Yes.
We mapped the geometry of reality on Barber's static bookshelf of Platonia. We discovered with Page and Wooders that quantum entanglement generates a local, internal perception of time.
Right.
And we just learned that to preserve causality, this entangled time must tick forward in discrete pixelated frames that perfectly adjust for relativistic speed.
We have thoroughly deconstructed time into quantum information and geometry.
But it begs the ultimate question. If reality is just a vast network of discrete, entangled quantum correlations, where does this network actually live?
What's the substrate?
Exactly. What is the physical architecture of the universe, storing all this information and generating the gravity we feel?
That brings us to the final framework in our deep dive today.
The quantum memory matrix, or
Yeah.
QMM.
If we connect this to the bigger picture, the QMM is an attempt to build a unified architecture of spacetime from the ground up using nothing but the concepts of information theory and quantum memory.
The sources describe the QMM framework by completely redefining what space actually is.
Space is not an empty void.
It's not just a theatrical stage where particles perform. Space is literally described as a vast lattice of finite capacity memory cells.
It is a cosmic hard drive.
The hard drive analogy is mathematically rigorous here, isn't it?
Very much so. The QMM relies heavily on a principle from black hole thermodynamics known as the covariant entropy bound.
Specifically the Begenstein bound, right?
Yes. This principle dictates that a given volume of space can only contain a finite maximum amount of quantum information. And that limit is determined not by the volume itself, but by the surface area bounding that volume.
Wait, really? So a cubic centimeter of space isn't infinitely divisible?
No.
It has a strict megabyte limit on how much data it can hold.
Exactly. The universe is a discrete grid of data storage.
And what is it storing?
It stores the records of quantum interactions. Every time two particles collide, every time a wave function collapses, every time a physical event occurs, it leaves a localized imprint of quantum information entanglement entropy within these memory cells.
And this data storage directly generates what we perceive as gravity.
Yes, the sources introduce this as the geometry information duality, or GID.
GID is a revolutionary perspective. It posits that the physical curvature of spacetime, which is Einstein's gravity, is not the warping of a physical fabric.
Curvature is simply the spatial variation in information density.
This is mind-blowing. So mass and energy aren't heavy things bending space.
Not fundamentally, no.
Mass and energy are just incredibly dense regions of stored data. The Earth is a massive clustering of quantum information, and its gravity is just the QMM lattice straining under the data density.
Gravity is the topography of information.
But if spacetime is a hard drive, How does time function within the QMM? It is no longer a one-dimensional coordinate line,
No, the sources state that in the QMM, time is a vector field.
a vector field.
We can denote this vector field as T sub A. A vector field assigns a direction and a magnitude to every single point in space.
Think of a weather map showing wind currents, right? The arrows point in the direction the wind is blowing, and their length shows the speed.
Exactly. In the QMM, the time vector field is determined by the gradient of informational entropy.
Let's unpack the gradient of informational entropy.
As physical events occur, they write new data into the memory cells. The local amount of stored information, the informational entropy increases.
Okay.
The time vector, T sub A, simply points in the mathematical direction of the steepest increase in the stored information.
So time literally flows in the direction that data is being written to the hard drive.
Yes.
Time isn't passing. The universe is just updating its memory banks,
The flow of time is the directional propagation of quantum updates across the memory lattice.
which radically redefines how we think about cause and effect. Normally, we view causality geographically.
Right. Event A is spatially next to event B, so A causes B.
If I drop a glass, it hits the floor directly beneath it.
But in the QMM, causality is completely divorced from geometric distance. It is defined entirely by informational adjacency.
Informational adjacency. Explain how two things can be adjacent without being physically next to each other.
Two memory cells in the universe are considered adjacent, meaning an event in one can causally affect the other only if they share mutual quantum information.
They must be entangled.
Yes.
So two particles could be sitting a millimeter apart, but if their quantum states are completely unentangled, they share no mutual information.
And therefore, they cannot causally interact. They are causally disconnected.
Wow. The underlying architecture in the universe is a web of information exchange, not a rigid geographic grid.
Precisely.
But I have a major pushback question on this vector field concept.
Go ahead.
If time is just an arrow pointing in the direction of increasing information, what happens when you push the system to the absolute extreme? What happens at the event horizon of a black hole?
Ah, the extreme limits.
Because the information density being crushed into a singularity is staggering. The data being written to those memory cells must hit that covariant entropy bound. Does the time vector field just break?
This raises an important question, and it is where the QMM framework actually shines. Because time is a local vector field driven by information gradients, it is not required to be uniform.
It doesn't have to point in the same direction everywhere.
Exactly. Near a black hole, the rate of information deposition is immense. The local gradient becomes incredibly steep and chaotic.
If a vector field gets distorted, time isn't just slowing down. The arrows are pointing in highly localized, disparate directions.
The math demonstrates that these extreme informational anisotropies, these chaotic local gradients, produce physical effects that mathematically mirror gravitational time dilation.
Right.
The slowing of time near a black hole isn't a physical stretching of the temporal dimension. It is the local informational update rate getting bogged down. The memory cells are saturated.
It's exactly like a computer freezing up.
Yes.
When your CPU is hit with too much data processing all at once, the frame rate drops, the mouse stutters, and the system lags. Gravitational time dilation is just extreme computational lag on the cosmic hard drive.
It is a sweeping reconceptualization of relativistic physics, translated entirely into the language of computation and data storage.
My mind is officially blown. We have dismantled reality down to the bolts today.
We really have.
We started with Newton's clock, moved to Einstein's malleable fabric, hit the brick wall of the Wheeler-DeWitt frozen universe,
Blurred our vision with Rovelli's thermodynamics.
stared at the static, asymmetrical bookshelf of Barber's Platonia, watched Page and Wooters entangle photons to simulate time, pixelated that time to save the math,
And finally rebuilt the entire cosmos as a quantum memory matrix.
where gravity is data density and time is the computational update of the hard drive.
It forces us to discard almost every intuitive assumption we have about the physical world.
But I know you, the listener, are sitting there asking the ultimate question right now. So, what does this all actually mean?
The practical application.
Yes. How does knowing that time is a vector field of quantum entropy gradients change my Tuesday? I still have to pay my taxes. I still have to go to the dentist. How do you live your life when physics tells you the passage of time is a persistent hallucination?
It is the most vital question we can ask. Physics is not merely abstract mathematics. It is the fundamental description of our existence.
Exactly.
The implications of these quantum temporal theories offer both profound philosophical comfort and highly practical insights into human agency.
I'm ready. Let's break down the major takeaways. What is the first paradigm shift for the listener?
The first major implication stems from Julian Barber's Platonia. We can call it the concept of immortality and presence.
Immortality is a very strong word for a physics discussion.
It is, but in Barber's framework, every possible configuration of the universe is a permanent static coordinate in the mathematical landscape of Platonia. That means no moment ever ceases to exist.
Ever.
The visceral human fear that the past is fading away or that time is slipping through our fingers is based on a false premise.
So the moment I learned to ride a bike, or a conversation I had with a grandparent who passed away, those moments aren't gone. They didn't burn up in the furnace of time.
They are not gone. They exist eternally as specific, highly structured time capsules within Platonia. They are just as physically real and permanent as the moment you are currently experiencing right now. You do not lose time. Your life is not a fleeting spark that flashes and vanishes into nothingness. Your life is a permanent, complex, geometric structure embedded forever in the eternal mathematics of the universe.
That completely shifts the emotional weight of time. If moments are eternal structures on a bookshelf, the goal isn't to desperately hoard time or mourn its passing. The goal is to maximize the quality of the now you are currently inhabiting.
Because whatever you build in this now is a permanent addition to the architecture of reality.
It mandates a radical, scientifically grounded form of mindfulness.
It truly does. And the second major implication comes from combining this with the QMM, focusing on agency and invention.
I was wondering about agency. Because if everything is just a frozen point in Platonia, it sounds highly deterministic. It sounds like my choices are already carved into the bookshelf, and I'm just reading a script.
It can appear deterministic from a purely classical view of Platonia. But when you introduce the quantum mechanics of the Page-Withers mechanism and the QMM, that changes entirely. Remember, time and causality emerge from the entanglement of quantum states.
Right.
The causal structure of the universe is actively built by informational updates.
So the hard drive isn't full. There are blank sectors waiting for data.
The future is radically open. We are not passive passengers sitting on Newton's uniform river of time being carried to a predetermined destination.
We are, through our conscious observations, measurements, and physical interactions with the environment, active participants in collapsing wave functions.
Yes, we are generating the entanglement that literally creates the local flow of time. Our conscious agency is a physical force expanding the informational lattice.
We are laying the track down right in front of the train as we drive it.
Precisely. We are actively weaving the temporal fabric. And this leads directly to the third and perhaps most actionable takeaway, the information imperative.
The information imperative, what is that?
If time is mathematically defined as the gradient of informational entropy, then the fundamental currency of the universe is information. Entropy, the thermodynamic blurring Ravelli talked about, is constantly trying to scramble that information.
Trying to turn the highly structured time capsules into a featureless, chaotic blur of heat.
Exactly. So what is our role in that cosmic struggle?
Our role as highly complex biological and social systems is to counteract entropy.
We do this by building and preserving stable structures. When you form a lasting memory, when you write a book, when you construct a resilient community, create art, or discover a new scientific principle, you are imposing order.
You are writing high-quality data into the quantum memory matrix.
Every time we preserve information against the decay of entropy, we are defining our place in the temporal flux. We are pushing back against the cosmic blur.
I absolutely love that framework for finding purpose. But I do want to touch on the purely practical day-to-day aspect of this too. I was reading one of the source articles on quantum time management, and I laughed out loud at a specific section. They proposed a strategy called quantum superposition scheduling.
Ah, yes, the superposition meeting.
The idea is, since time only emerges from quantum entanglement and observation, you should schedule a terrible meeting, but never actually confirm it.
You leave the meeting in a state of quantum superposition.
Right. Until the participants forcefully collapse the wave function by actually showing up in the conference room.
It is a delightful, if entirely impractical, corporate joke, but there is a serious underlying truth buried in the humor there.
Which is?
The sources suggest that our level of conscious engagement profoundly alters our perception of the temporal flux. If the flow of time emerges from the density of quantum correlations, then engaging deeply with a complex task, entering a state of intense psychological focus or flow, that might conceptually correlate with increasing the density of quantum entanglement between your cognitive processes and your environment.
Like We are overclocking our local processor on the QMM hard drive, writing data at a massive rate.
When you are in a state of deep focus, you are generating dense informational exchange. This high rate of data processing alters your local temporal vector field. It is the underlying physical reason why, subjectively, time seems to wildly distort, speed up, or disappear entirely when you are deeply in the zone.
So the self-help advice to be present isn't just about lowering your heart rate. It is a method for actively manipulating the quantum informational topology of your local spacetime.
A rigorous physicist might balk at the exact phrasing, but conceptually, the parallel holds. We do not live in time as a container.
No.
Time is the pattern by which our universe's information evolves, and human consciousness is an integral data processing component of that vast computational network.
That is absolutely staggering to contemplate. We started this deep dive looking at the watch on our wrist, assuming that the ticking seconds were an absolute tyrant ruling over reality.
And we found something else entirely.
We've unpacked a universe where that ticking is just a beautiful, persistent illusion. It's a hallucination born from our blurred macroscopic perspective, driven by the quantum entanglement of internal clocks and systems,
Ticking forward in discrete, pixelated Planck scale frames.
and ultimately manifesting as a vector field of information updates on a cosmic hard drive.
It is an intellectual journey that completely dismantles our common sense intuition, only to rebuild our understanding of reality on a foundation of profound, fundamental interconnectedness.
I feel like I need a nap.
Well, before we finish today, the quantum memory matrix framework offers one final, highly speculative extrapolation that I want to leave the listener with, something truly mind-bending to mull over.
Lay it on us.
If the universe truly acts as a massive computational matrix, and if causal order is dictated purely by informational entanglement rather than a rigid geometric timeline,
Yes, what does that allow?
it forces us to consider the mathematical possibility of quantum recursion.
Quantum recursion. In computer science, that's when a function feeds its output back into its own input. It creates a loop.
Exactly. In a classical Newtonian timeline, cause must strictly precede effect. It is a one-way street.
Right.
But in the informational topology of the QMM, if complex quantum information can be retrieved, coherently superposed, and fed back into prior adjacent informational layers of the network, the strict impenetrable boundary between the past and the future begins to dissolve.
Wait, are you talking about retrocausality, the future mathematically influencing the past?
The fundamental mathematics of the QMM do not strictly forbid it. If the entire history of the cosmos is stored as discrete, entangled imprints on a quantum lattice, and causal paths are simply links of mutual information, it is theoretically possible that highly advanced quantum states could entangle with, and thereby retroactively influence, prior informational configurations.
So if we look back at Barber's vast eternal bookshelf of Platonia, the ending of the book might be actively, quantum mechanically rewriting the beginning as we read it.
It is a deeply speculative, highly controversial idea at the absolute fringe of the discipline. But in a universe where time is not a physical law, but merely a vector field of information, it suggests that the architecture of reality might not be a straight line.
It might be a closed loop.
An ongoing, eternal dialogue between what was, what is, and what will be, all echoing simultaneously through the deep structures of Platonia.
The future rewriting the past. I think I need to sit in a quiet, dark room and just stare at a wall for an hour to process the implications of that.
It is an overwhelming amount of conceptual reality to process at once.
It really is. But it's also incredibly empowering. I want you, the listener, to do what we did at the very beginning of this deep dive. Look at your watch one last time, watch the second hand move, feel the time pass. But this time, realize that the flow you are feeling isn't a relentless river carrying you away toward the end.
It is just the universe computing itself.
It is the sound of the timeless bronze bell ringing in your awareness. It is the active entanglement of your consciousness with the cosmos, writing the very next line of code onto the cosmic hard drive. Thank you for joining us on this deep